Okay, in this lesson we are going to be looking at least squares regression lines or linear regression lines or trend lines. All of those words are interchangeable, but basically we're going to graph some data. We're going to draw a line that sort of best fits the data, so it could be called a line of best fit also. And then we're going to use that line to make some predictions, okay? So what I'm first starting out with here is a problem about fuel efficiency. And I've looked at some various cars based on the year that they were built, and then looked at the fuel efficiency, which is how many miles per gallon that they get, okay? And you can see that when you plot those points, for instance, I plotted the point in 1960 and 15 and a half, and I plotted the point in 1970 and 14.1. So those are all plotted for you. You can see that when you do that, it looks like as years pass and in more recent years that the fuel efficiency or the number of miles per gallon increases, okay? There's a general trend that as time passes, miles per gallon fuel efficiency is getting better, okay? So what we want to do is we want to come up with an equation that we can use to kind of predict the fuel efficiency in any given year. So you want to draw a line that sort of averages out this data, okay? And so I am going to draw a line that looks something probably about like that, and I just really kind of drew that sloppily, but it kind of averages out the data in there and lets me sort of use it to make a prediction, okay? We want to come up with an equation for that line, which means I need to find 2 points that are on that line somewhere. You can pick any 2 points you want. I'm going to go ahead and pick this point right here, which is the year 1960 and 12 miles per gallon. By the way, I should probably have this axis labeled with miles per gallon. And then I can pick any point I want. I could certainly do this one if I wanted because it's on there, which is the year 1970 and 17. Or I could do this one, which is the year 1990 and 27, it looks like. Okay, so I'm just going to use those 2 points. You could pick any ones you want. Doesn't matter. I will use those two. So 1960 and 12. And 1997 and, 1990 and 27. All right. Obviously, one thing you need to know about the line is the slope. So I'm going to go ahead and calculate the slope. The slope will be your y2 minus y1 over x2 minus x1. Okay. So in this case, I will have my y, the difference in y's, 27 minus 12, over difference in my x's, which would be 1990 minus 1960. So 27 minus 12 is 15, 1990 minus 1960 is 30, and that reduces to 1/2. Okay, so your slope will be 1/2. All right, now that I know that, I'm going to go ahead and use my point slope formula. Since I actually have 2 points I could use, I will use my m, which I already calculated to be 1/2, and I'll use either one of the points. I'm just going to go ahead and choose to use this one. You could use either one. It doesn't matter, okay? So I am going to do y minus y1, which is 12, equals my slope, which I just calculated to be 1/2, minus my x1, which is 1960. I'll distribute that 1/2 through. So I'll have 1/2 x, and then half of 1960 would be 980. Okay, add the 12, and I will get y equals 1/2 x. Negative 980 plus 12 is negative 968. Okay, so that right here would be the equation for that red line that I just drew. That's the equation for it. Now, when we are doing least squares regression line or linear regression or line of best fit or trend line, what we're going to do above that equation is we're going to put a little, what's called a hat above there. The reason we're putting the hat above there is because that line does not perfectly fit the data. It's just our best prediction. And that hat means that we're using it to make a prediction. We're making a guess with it, a good guess, but it's still a guess. okay? If I wanted to write that line in function notation, instead of y right there, I would just have us put f of x with the hat above it still, because again, we're making a prediction with it. It's not guaranteed to happen, okay? So that's what that would look like. And then I'm going to tell you one other thing that I think is actually, in people in the stats world think that this method is even better. We're still going to put the hats above there, but if I were looking at that equation right here, I don't even know what y and x are. I don't know the context of this problem. So instead of putting y and x in there, I actually want you to look at what's on your x-axis and what's on your y-axis. So on your x-axis is years, and on your y-axis is miles per gallon. So I would actually prefer that you write your equation like this. Y-axis was miles per gallon, and then my x-axis was what year it was, and this actually is the best equation that you could write, okay? Next, what is the slope of the line? We already know that the slope of the line is 1/2, so that much I know, and that part won't be too much of a problem. The problem that you will maybe have is figuring out what it means, and this is a little bit tricky, okay? We know that slope, one of the ways to think about slope, we know that slope is rise over run. We know that slope is the change in your y value over the change in your x value. That's one of the definitions of the slope you learned way back in middle school, or even maybe in elementary school, I don't know, okay? Then I want to put this in context. So along your y-axis, again, was miles per gallon, and along your x-axis was years. Okay, so what this means is the top represents your change in miles per gallon, the bottom represents your change in years. So you can see that my miles per gallon goes up 1 every time my year goes up 2, since they're both positive. Okay, so I'm going to write a little sentence about it that looks like this. Miles per gallon is predicted, it's not guaranteed to happen, because remember, this is just a trend line, is predicted to increase by 1 mile per gallon for every 2 years. Okay, something like that. All right, then if you wanted to predict the fuel efficiency in 1985, what would you do? So luckily I have this handy dandy little equation that I made right here, which I'm going to go ahead and copy. Okay, again, once you put things in context, it's really easy to know what to do, because what I'm given is a year here. So I'm given the year 1985, and now I know exactly where I should put the year. The year is going to go right there. So miles per gallon will be 1/2 of 1985 minus 968. And when you punch that all in, you should get about 24.5 miles per gallon. Okay, again, it's a prediction. Okay, it's predicted to be about 24.5, so I'm going to put that little swirly for close to. Okay, then in the next problem, if you wanted to predict the fuel efficiency to be 26 and wanting to know when that would happen, then what would you do? Again, we have this handy dandy little equation right here. Okay, and I want the fuel efficiency, or the miles per gallon, to be 26. So I can go ahead and take that 26. I know right where to put it. And I will do, instead of writing year, I am just going to write X right here, just so that I can solve this a little bit easier. Okay, so I would add the 968 and multiply by 2, and X over your year, in this case, would come out to be pretty darn close to 1988. Okay, And then, does it make sense to use this line of best fit or least squares regression line to predict the fuel efficiency in the year 2020? And the answer to that is no. We only use it to make predictions within the observed data. Okay, here's what that means in English. We have gathered data anywhere from the year 1960 to the year 1990. Our earliest data point was in 1960 and our latest data point was in 1990. If we wanted to go just a little bit under 1960 and just a little bit over 1990, we'd probably be okay. But anything much past that range will give us really inaccurate predictions, and that's called extrapolation, which is a big fancy word you'll learn later, but that's what that is, okay? So we would not recommend doing that. This, oh, you know what? I'm going to go back and I'm going to teach you how to do this on your calculators really quick, okay? We want to know how accurate our prediction line is compared to what the calculator would give us. I will tell you the calculator is always going to be way, way, way more accurate. So although I taught you how to do this by hand, and it's good to know what we're doing, your calculator is always much more accurate. So I want you to turn your calculators on, and I'm going to teach you how to get a more accurate answer that way. Okay, so here's the first thing you need to do. You need to enter your data in. So you're going to press the stat key, which is right, the one that turned red. Okay, and then you're going to go ahead and hit edit. And you can see that you have a bunch of data in a bunch of different lists. Okay, so we're going to, for this problem, use list 1 and list 2, which means I need to clear the data that's in there out. To clear data, do not hit the word or the delete button. Do not do it. Up arrow until the name of the list is highlighted. Go ahead and hit clear and enter. And now you'll see all your data is gone, and I'm going to go ahead and do that with list 2 also. So up arrow until the name of the list is highlighted, hit clear, not delete, and enter. Okay? If you hit delete, your entire list will be gone. So now we want to enter this data in. I'm going to put the years in list 1. So this is 1960, and you guys can go ahead and hit pause and do this if you want. You'll probably be faster at it than I am because on the overhead projector, it takes on the smartboard, not overhead projector, it takes a long time. All right, and then list 2. All right, really important to make sure that your data is in there accurately, because if your data is not accurate, your line won't be accurate, okay? So there it is, we've got our data in, and now we want to calculate the linear regression line. So now we're going to go stat, over to calculate, to number 4, okay? And what you want to pay close attention to is what's listed right here. You want to make sure that your X list, what was along your X-axis, is in list 1 and that's in list 2. If you, for whatever reason, typed them into different lists and you need to change that, for instance, here's list 3 right here. So if I wanted to change that to list 3, since it's blue, I could go second and number 3. Oops, sorry, I have to get this out of here. One more time. Second and number 3. One more time. Second, 3. There we go. List 3. Okay, I don't want list 3. I want list 1. So I'm going to go second, number 1 again, and make sure that my data is in list 1 and list 2, which it is. And then you're just going to simply go ahead and go down to calculate. And it will spit out an equation like this. You can see that you are used to having y equals mx plus b. That's what you're used to. They use a for m. So this number right here is their slope, and this number right here is our y-intercept. Now when we did it, we got a slope of 1/2, and we got a y-intercept of negative 968. So you can see that our line is a little bit off from theirs, which we would expect, but theirs is much more accurate, okay? So that's just a quick little version on our calculator. All right, then next I want you to know that this problem we will do here is it just, we're going to use it only on our calculators because our calculators are accurate, but it's asking us to make a prediction. This problem is about how old husbands and wives are when they are married. Notice that the husband is along the x-axis and the wife is along the y-axis. And I'm wanting to know if a husband is 35 years old, how old should a wife be? Okay, we're going to use our calculators to do this since this is the most accurate way to do this. And so again, we need to enter our data in. I want you to notice that for this data point down here, you have an X value, but you do not have a matching Y value. So when you enter this data into your list, don't enter the 35 into list 1 because it has to have a matching Y value or you're going to get an error on your calculator, okay? So don't enter the 35 in when you enter your data, all right? So here we go. Again, we're going to go Stat, Edit to enter our data. We'll right arrow or left arrow over up until the name of the list is highlighted, hit clear and enter. And I'm going to do that for list 2 also. Okay, and then I can go ahead and enter this data in. So I have 19. And again, I'm not going to enter the 35 in because I don't have a match for it. All right, so my data's in. And now I will do Stat, over to Calculate, number 4 for linear regression. My data's in list 1 and list 2, so that's good. And I'm going to go ahead and hit Calculate. All right, so here's what my equation would look like now. In y equals mx plus b form, it would look like this. Y equals my m, which is the a for them, would be 0.966x plus my b, which in this case is negative 0.242. Again, this is a prediction line, so you're going to use a hat, and then it's much better if you actually put this in context. So on this particular problem over here, the husband was the X and the wife was the Y. And so instead of putting Y there, I am going to do this. The Y value is the wife's age. Okay, so the predicted wife's age would be 0.966. My X is the husband's age. Minus my y-intercept, okay? This is the trend line, the equation, or the line that best fits this data, that looks, that best averages out that data, okay? So there it is. Now, I haven't answered the question yet. The question is, if the husband is 35, how old will the wife be? And so I will just take that 35, I will stick it right in here, and I will go ahead and calculate that. And when you calculate that and you simplify that, the wife's age will be about 33.568 years old. Okay? And that should do it for this lesson.